Is there a difference between a state function which consists of a superposition of the up and down spin with equal amplitudes, and a statistical mixture of up and down spin states? In the previous video, we show that these two states are represented differently in terms of their density matrix. Most notably, the system on the left contains non-zero off-diagonal components in their density matrix, which we attributed to the coherence between the up and down spin, while the system on the right has zero off-diagonal terms. In this video, we shall use this example to exemplify the difference between these two states, and how the coherence influences the measurement results of their spin observables. First, we write down the matrix representation of the observables of the spin components x, y, and z. These spin operators are written in terms of the Pauli spin matrices. And we also state their respective eigenfunctions for their respective eigenvalues of plus and minus 1. In the first system, we consider a coherent superposition of the up and down spins, with amplitudes alpha and beta respectively, whose modulus square sums are normalized to 1. This is a pure state, and its density matrix is simply given by its outer product, and is given as shown. Most notably, it contains off-diagonal elements given by the product of the two amplitudes, which describe the coherence between the two spin states. In the second system, we consider a statistical mixture of up and down spins. The density matrix in this case will just be diagonal, where the diagonal elements account for the proportion of the spin up and down mixture. The off-diagonal elements in this case will be 0, since this is a classical mixture and there is no coherence between them. Let's first compute the observable spin z component for the two states. This is given by the trace of the product of the density matrix with the observable. The result is rather straightforward, which in both cases are the same, and is given by alpha modulus square minus beta modulus square. If alpha equals to beta, then the expectation value of the spin z observable will be 0. This is expected since the up and down are weighted equally, whether in the pure state or statistical mixture. Hence their expectation value for the spin z observable should be 0. Now, let's see what happens if we compute the expectation value of the spin x observable instead. Recall that in the two systems, we prepare them in the z spin eigenstates. One a coherent superposition of plus and minus z eigenstates, while the other is a statistical mixture. We show in the previous slide that these two systems yield exactly the same result if we perform measurement of the z spin observable. Now, we see that the expectation value of the x spin observable is not the same. In the system with statistical mixture, we yield 0. In other words, if we perform measurement on an orthogonal spin axis compared to the one we prepared the state in, we will yield an expectation value of 0. However, the system with the pure state prepared as a superposition of the up and down spins instead yields a finite expectation value for the x spin observable. And that value arises from the off-diagonal part of the density matrix, which clearly indicates that it is a result of coherence. In fact, we can see that the x spin's eigenstates can be composed of the superposition of the z spin's eigenstates. Here, we summarize the key results of this example. We consider a system of a pure state consisting of superposition of the z spin eigenstates, and a system which is a mere statistical mixture of them. We show that their expectation value on the z spin, the spin axis on which they were being prepared, yielded the same result. However, the results differ when measurement is made on the other spin observable components, clearly highlighting that the two systems can be physically differentiated in experiments. Stay tuned, and subscribe, so you will be notified of our future episodes. Join our Free Science Academy Discord channel to discuss science and technology. High school students are welcome to join and post your questions, we will answer them during our free time.